Affine differential geometry is a type of differential geometry in which the differential invariants are invariant under volume-preserving affine transformations. The name affine differential geometry follows from Klein's Erlangen program. The basic difference between affine and Riemannian differential geometry is that in the affine case we introduce volume forms over a manifold instead of metrics. Preliminaries. Here we consider the simplest case, i.e., manifolds of codimension 1. Let Mrn plus 1 be an n-dimensional manifold, and let Xi be a vector field on Rn plus 1 transverse to M such that Tprn plus 1 equals Tpm span for all Pm, where denotes the direct sum and span the linear span. For a smooth manifold, say N, let psi denote the module of smooth vector fields over N. Let d psi times psi be the standard covariant derivative on Rn plus 1 where d equals dxy. We can decompose dxy into a component tangent to M and a transverse component parallel to Xi. This gives the equation of Gauss. dxy equals xy plus hxi, where psi times psi is the induced connection on M and h. Psi times psi r is a bilinear form. Notice that and h depend upon the choice of transverse vector field Xi. We consider only those hypersurfaces for which h is non-degenerate. Interestingly, this is a property of the hypersurface M and does not depend upon the choice of transverse vector field Xi. If H is non-degenerate, then we say that M is non-degenerate. In the case of curves in the plane, the non-degenerate curves are those without inflections. In the case of surfaces in 3 space, the non-degenerate surfaces are those without parabolic points. We may also consider the derivative of Xi in some tangent direction, say x. This quantity, dx Xi, can be decomposed into a component tangent to M and a transverse component parallel to Xi. This gives the Weingarten equation. dx Xi equals minus sx plus tau Xi. The type tensor S. Psi is called the affine shape operator, the differential one form tau. Psi r is called the transverse connection form. Again, both S and tau depend upon the choice of transverse vector field Xi. The first induced volume form, let omega psi n plus 1 r be a volume form defined on Rn plus 1. We can induce a volume form on M given by omega psi n r given by omega equals omega. This is a natural definition. In Euclidean differential geometry where Xi is the Euclidean unit normal, then the standard Euclidean volume spanned by x1, xn is always equal to omega. Notice that omega depends on the choice of transverse vector field Xi. The second induced volume form, for tangent vectors x1, xn let H equals B the n times n matrix given by high J equals H. We define a second volume form on M given by nu psi nr, where nu equals det 1/2. Again, this is a natural definition to make. If M equals Rn and H is the Euclidean scalar products, then U is always the standard Euclidean volume spanned by the vectors x1, xn. Since H depends on the choice of transverse vector field Xi, it follows that nu does too. 2 natural conditions. We impose 2 natural conditions. The first is that the induced connection and the induced volume form omega be compatible, i.e., omega 0. This means that x omega equals 0 for all x psi. In other words, if we parallel transport the vectors x1, xn along some curve in M with respect to the connection, then the volume spanned by x1, xn, with respect to the volume form omega, does not change. A direct calculation shows that x omega equals tau omega and so x omega equals 0 for all x psi if, and only if, tau 0, i.e., dx Xi psi for all x psi. This means that the derivative of Xi, in a tangent direction x, with respect to d always yields a, possibly 0, tangent vector to M. The second condition is that the 2 volume forms omega and nu coincide, i.e., omega nu. The conclusion it can be shown that there is, up to sign, a unique choice of transverse vector field xi for which the two conditions that omega0 and omega nu are both satisfied. These two special transverse vector fields are called affine normal vector fields, or sometimes called Blaschke normal fields. From its dependence on volume forms for its definition, we see that the affine normal vector field is invariant under volume-preserving affine transformations. These transformations are given by SLRn plus 1, where SL denotes the special linear group of times matrices with real entries and determinant 1, and denotes the semi-direct product. SLRn plus 1 forms a Lie group. The affine normal line. The affine normal line at a point Pm is the line passing through P and parallel to xi. Plane curves. The affine normal vector field for a curve in the plane has a nice geometrical interpretation. Let IR be an open interval and let gamma IR2 be a smooth parametrization of a plane curve. We assume that gamma is a non-degenerate curve, i.e., is without inflection points. Consider a point P equals gamma on the plane curve. Since gamma is without inflection points, it follows that gamma is not an inflection point, and so the curve will be locally convex, i.e., all of the points gamma with t0 minus epsilon less than t0 plus epsilon, for sufficiently small epsilon, will lie on the same side of the tangent line to gamma at gamma t0 minus epsilon less than t0 plus epsilon. For parallel lines sufficiently close to the tangent line, they will intersect P in exactly 2 points. On each parallel line we mark the midpoint of the line segment joining these two intersection points. For each parallel line we get a midpoint, and so the locus of midpoints traces out a curve starting at P. The limiting tangent line to the locus of midpoints as we approach P is exactly the affine normal line, i.e., the line containing the affine normal vector to gamma at gamma. Notice that this is an affine invariant construction, since parallelism and midpoints are invariant under affine transformations. Consider the parabola given by the parametrization gamma equals. This has the equation x2 plus 4y2 minus 4xy minus y equals 0. The tangent line at gamma has the equation y equals 0, and so the parallel lines are given by y equals k for sufficiently small k0. The line y equals k intersects the curve at x equals 2k plus or minus square root k. The locus of midpoints is given by k0. These form a line segment, and so the limiting tangent line to this line segment as we tend to gamma is just the line containing this line segment, i.e., the line x equals 2y. In that case, the affine normal line to the curve at gamma has the equation x equals 2y. In fact, direct calculation shows that the affine normal vector at gamma, namely xi, is given by xi equals 2 minus 1/2. In the figure, the red curve is the curve gamma, the black lines are the tangent line and some nearby tangent lines. The black dots are the midpoints on the displayed lines, and the blue line is the locus of midpoints. Surfaces in 3 space. A similar analog exists for finding the affine normal line at elliptic points of smooth surfaces in 3 space. This time one takes planes parallel to the tangent plane. These, for planes sufficiently close to the tangent plane, intersect the surface to make convex plane curves. Each convex plane curve has a center of mass. The locus of centers of mass trace out a curve in 3 space. The limiting tangent line to this locus as one tends to the original surface point is the affine normal line, i.e., the line containing the affine normal vector.